So that's also a much bigger population. There's like 20-something vision students every year, and a third of them are doing some kind of robotics or RL related thing. That also adds up. I saw that, was it Russ and Katerina at CMU were actually teaching a deep RL class?
They actually Katerina, borrowing a lot of John's lecture material, at least I saw for the policy gradient side of things.
Did they end up posting videos for that, or is it all?
I don't think I've seen videos, but like they definitely have the lecture notes. And I think like she relayed all of them and stuff, but like the material exposition is
And then Emma Brunsk lectures a class at Stanford. It's not a deep RL class, but it's just an RL class in general, but it has like about half of it at this point and more recent deep RL stuff. So I actually gave a talk, a guest lecture there last year with Chelsea.
Those are considered lectures. I actually like also ended using that for the course. Yeah, I think like that's good.
This is the triple AI in Australia that you had to bail from.
I saw your post and I was like,
All right, I think we can probably get started. All right, so we're going to start. It's my pleasure to introduce today Igor Mardach. Igor did his PhD at the University of Washington with Emanuel Todorov and Zoran Popovich in computer graphics and things related to computer graphics. And then a postdoc here at UC Berkeley with Professor Peter Abiel. And currently he is a researcher at OpenAI.
Cool. Thanks for that introduction, Sergey. And today, just give me a moment to touch the microphone. Is this all right? Okay, great. Today during this lecture, I'll talk to you a little bit about optimization and reinforcement learning in multi-agent settings. And the theme of the work is going to be to use optimization as a principle underlying much of natural behavior. So in just standard single agent settings, to briefly review, we're, at least at OpenAI, the way that we're seeing things is we're seeing optimization and reinforcement learning as a method to generate different behaviors. So you give a cost function and outcomes a particular movement. And so it's a very automatic and flexible approach. The behavior is a result of optimizing a cost function, but you don't actually say any details of how that behavior is generated. So it's also a very concise and flexible description. And just to make sure that we're on the same page, I mean, I think this is going to be a review from a lot of the previous lecture material in this course, but just kind of my take on it is how would you use optimization to create behaviors in movement? Let's say you start out in some initial state x0 and you want to get to some target state. Well, you can pose an optimization problem where you can optimize for a sequence of states or potentially policy parameters that, when rolled out under forward dynamics, result in some trajectory. And then you say you put a cost function that says, well, how close, for example, you are to the target or any other metric of success that you can think about. And so, for example, the states here, the x's, can be referring to, say, the joint angles or configuration of some particular robot. And so it's like standing before a ledge, and for the target, you want it to be standing over a ledge, for example. And applying the principle of optimization, interesting. Do the videos not
Terminal location of the capsule. Nothing is specified about the motion of the character. and a strategy of having to pick
where
up
it's coming
and carry
from.
the
But,
object emerges automatically.
You can generate all of these behaviors largely automatically without specifying the minute details of how the character should be moving. It also allows you to perform various virtual experiments to test hypotheses. So for example, if you can have a model that predicts walking under Earth gravity with a particular algorithm, you can then start asking questions. Well, how would this character walk under moon gravity or under any other conditions? For example, if its body was changed, or how would the movement be affected by noise in the environment? So, for example, without noise, you might be taking very large steps. And with environment noise, you might be moving much more conservatively. But that was all for single agent settings. And what about multi-agent behaviors? And this is a line of projects that we've recently at OpenAI, in collaboration with a lot of great students at Berkeley, have been pursuing. And well, first, why? What's the motivation for multi-agent? Well, there are a couple of reasons. The first is that multi-agent setting provides a much richer set of possible behaviors because, if you, for example, want to run virtual experiments, well, there's only so many different things that you can explore with just a single agent in acting in the environment. What if, for example, you want to be exploring how multiple agents interact with each other in multiple ways, like potentially in terms of information transmission, like communication, which is what I will talk a little bit about later, in terms of social interaction between agents. Is there going to be any sort of social hierarchy or niches forming in multi-agent populations? These are all questions that you can start asking that you weren't able to ask in a setting where it's just one robot in the environment. The other motivation also is the multi-agent setting can be very useful environment for training intelligent agents. Like even if at the end all we cared about is a robot that can perform tasks very well, the multi-agent setting basically says that the environments can be pretty simple, actually, and a lot of the complexity can be arising from the agents trying to either cooperate or compete or basically interact with each other. And it also provides a natural curriculum because early on, the agents start out very, very simple, very basically. They may not have a lot of skills, but then as one gets smarter, that provides the pressure for the other agents to also get smarter to keep up with it. And the agents can potentially be jointly increasing in complexity as a result of these interactions. And we've kind of seen examples of this in optimal control before as well. So for example, like adversarial control methods where, or even for generative models, generative adversarial networks, like methods where you have basically a player, like a discriminator and a generator, or like a policy, and then the adversarial noise setting that lead to more robust behaviors at the end. These are all, I would say, special instances of the multi-agent setting. And the last motivation is that it also has the potential to have our artificial agents be interacting with humans down the road. Because if we're going to be making minimal assumptions about what the nature of these agents is, well, at some point we can just swap in one of the agents for the human. And if the algorithms need to be robust to interact with all sorts of agents, well, they potentially would then be able to interact with a human. And I think that has benefits both for human-robot interaction, for example, but also for safety reasons. So let's think about, by the way, any questions on this general high-level motivation? Feel free to interrupt. Yeah?
So when you say that multi-agent setting can potentially transfer to robot-human interaction, how critical is that and his inconsistencies, etc., in this multi-agent setting?
That is going to be an important part, yes. So a lot of this, I should also say, this is kind of like longer term motivations. I will not talk about solutions to all of these questions during this lecture. I think right now the hunch potentially, or the reasoning, the thinking that we're going with is, rather than trying to model a human accurately, you're just going to take an ensemble approach where you may assume that you would not be able to model the human very accurately, but you would want to be robust to all sorts of different models of others. So that's like robustness rather than accurate, robustness to noise or error rather than accurate modeling is the approach that we're taking. Great question, though.
You talked a little bit about like natural curriculum when you're talking about like different agents competing with each other, sort of thing. Is that necessarily a competitive kind of thing, or could you, I guess, is it possible to frame it, or have you thought about framing it as I guess, agents cooperating or something?
It can definitely be framed cooperatively, and I think like there will be these pressures for the agents to get smarter in the cooperative settings as well, and a couple of them, actually most of the settings I will talk about will be cooperative settings.
Okay.
Did you have a question?
Actually, I had a similar question.
Oh, okay, cool. All right, so now let's talk about the how. What's the simplest way that we can think of? Like, we've seen this optimization problem for generating just standard single agent behavior. So what about multi-agent behavior? Well, one very, very simple, like the first thing that you might think of is basically just do joint optimization, where you just have the state of the system just be the state of both agents, and the actions will just be concatenated vector of the two agents or however many agents that you have. And then you have exactly the same optimization as before. And that actually does produce, I don't know why the sound is playing. It produces reasonable and actually pretty interesting behaviors where, here the goal is to pass the box from one location to another, and you kind of see these cooperative behaviors of agents moving one thing to another. Or, you can think of multiple hands as being multiple agents, and again, they also kind of can jointly coordinate to perform these dexterous tasks.
Is it fair to call it multi-agent if they're being optimized by the same optimizer?
Nope. Which, okay, it won't lead to exactly the point that you're just asking. 2 slides later, it will lead to the point that you're asking, that you've mentioned. But I would not say that it does. I think one interesting thing that it can give you, though, is that this goal-driven movement, here you had physical constraints. And these constraints in the physics and the tool of optimization is what leads to interesting behaviors. So, for example, if you didn't have the constraints of physics, you could just have the agent flying towards the goal, and hey, your problem is solved. But that's not a very interesting solution. And actually, adding in the physics constraints is what leads to the agent to figure out these strategies of like climbing over things and making these hands and foot placements. But what makes this problem uninteresting is that, precisely as you said, the joint state and action is just basically the same as a single agent problem. And you have centralized planning and centralized execution algorithm doing all of this. So I think there's only so many interesting things that there's only so many interesting questions you can ask in this setting. Which brings me from goal-driven movement to this part of the talk, which is goal-driven language. That's a project that we were working on some time ago, where we are now, for example, interested in a decentralized setting where you don't have one shared brain and you don't have this agents that just know what is what the other one is doing and thinking, then some form of communication between the agents is going to be necessary to coordinate them successfully. But the flip side is that this necessity to accomplish goals and coordinate will hopefully lead to the formation of language or some kind of communication between the agents. Much like the physics constraints led to interesting physical behaviors, the hope is that these communication constraints will lead to interesting linguistic behaviors. And in a recent paper, John Gauthier and myself argued for this definition of language understanding, that the agent understands language only when it can use it to effectively cooperate with other agents. And this is, as opposed to definitions of language understanding based on, say, predicting the next textual utterance or based on any of these predictive models, which are still useful, but we're just taking a different approach. And this idea is not new. I mean, people in linguistics and evolutionary linguistics have been talking about this since the 60s or even earlier. But I think the interesting thing is, like, now we have the reinforcement learning and the optimization tools to start tackling this question. Yeah.
So when you're talking about language, is it actually like verbal language, or is it more like a bit stream of my state and your state, and people just like agents just passing around their state?
So we'll see this in detail when I talk about the details of the project. Short answer is it is bitstream, or it's like a symbol, 1 out of k symbol stream over time, but it will have a lot of the structures of human language, as you will see. But before I get to that, I think an interesting question to answer is, what kind of languages do we hope to learn out of this goal-driven approach? And to answer this, it's been instructive to look at individual words in some simple language and then think about what are the goals that actually drive the creation and use of these words. And so for this, we looked at simple English. It was a subset of English created in the 1930s, mostly to introduce non-native speakers, to get them up to speed to learning English very quickly. And it consists of 800 English words, which are separated into 100 operational words, which are just very, very important core, you need this for everything words, and then 700 general words. And a large number of Wikipedia articles have been written in this language, so that's a sign that you can express a lot of the concepts in this language. So let's take a look at some of these 100 operational words first. I've kind of informally grouped all of them into things like spatial relationships, temporal relationships, group relationships, commands, causality, and reference. And just taking a look at, say, one of them, commands. Well, for a particular word like go, I guess that's a straightforward one. We could see that we could set up a scenario where you might have an agent or two agents, like a speaker and a listener agent. And the speaker agent wants the listener agent to go to some particular location, like a green landmark. And that would, to unambiguously give that command, it would necessitate the use or creation of a word like go or move or something like that. Similarly, you could think about things like if you need to move a particular object towards another, it might necessitate, say, the use of a word like put, or to utter particular symbols or utterances. You might have to use a word like say. Similarly, to give one thing to agent B, you could potentially also use the word put in here, but and for spatial relationships as well. A word like between, you might give a task, a speaker might give a task for the listener agent to go to this particular location. But what's the way to unambiguously identify it? Well, it might necessitate a word like between blue and green landmarks to identify that particular location. Or you can't rely on colors to do the separation. You might have to end up using a word like west, north, or south. Similarly, for things like near or far, you can create scenarios. Also for temporal relationships, things like before and after could be captured out of this goal-driven framework. Group relationships as well, like together would be go to particular location, or reference like this or you. Similarly, concepts like little or big, or every, or inquiry and all. So I think we're pretty confident that you could create scenarios that can capture a lot of these. I think I would say almost all of these, plus or like some synonyms of them. These 100 operational words. But what about the rest of those 700 words, where you have words like advertisement or digestion or industry and shame? Are you going to create a complex world that has, advertisement in it and then point to it like, hey, that's advertisement? Or are you going to be creating like the processes of digestion and modeling them in your agents just to be able to invent a word for it? You could, but that's a risky road. That's a risky research direction to go down on. So what we are considering right now is taking a two-stage approach to it, where you try to understand these 100 or more basic operational words grounded from physical experience, out of necessity, and then use these operational words as scaffolding to teach the subsequent words in the language. So for example, have never seen an alligator, but somebody who has can potentially, just using language, give me a pretty good understanding of the concept, like it's green and slithery and chases me or such. So I'll talk a little bit about the first part of it, and the subsequent parts of it we're working on right now. But for this basic understanding of words, we were looking at a pretty simple multi-agent environment, which is just basically a 2D world where you have agents of various colors and you have landmarks of various colors. And an agent has a physical 2D position and also a gaze location, and is also able at every time step utter a particular abstract symbol C. And so it's just an abstract symbol like 1 out of k, like 1 out of 100 possible symbols, and there's no other meaning assigned to it. And we can just see, oh yeah. And so just like what a single agent setting looks like is if you have various tasks like look at a particular location, or do nothing, for example, also can be a task, or move to a particular location, we can see the agent is successfully able to satisfy these goals, because that's pretty straightforward. There's no surprises there. We're just using standard optimization tools to do this. But extending it to the multi-agent setting is nothing terribly complicated. It's all reasonably straightforward, where you have the physical state of the action for every agent S, and every agent is able to make a physical action, but it's also able to make a communication action, which is this discrete action of uttering 1 out of 100 symbols or so. And you have n of these states for an agent. The dynamics functions, of course, depend on the states of all agents. The agents also have internal memory, which is basically recurrent neural networks. The agents are able to observe the physical states and also the communication utterances of all the other agents. And the policy is just going to be a mapping from these observations to the physical actions and communication utterances and memory updates. Oh, I should also say that in this work, we had the agents just have one shared reward. So the entire population basically has the same reward. Like the student or the listener agent needs to, say, get somewhere or something needs to happen. And this is kind of what, for between any two time steps, the computation graph looks like. And for policy optimization, in this particular work, we basically just use chain rule or use backpropagation through time. There was no need to use, I mean, in the later work that I will talk about, we used policy gradient or special extensions of policy gradient methods. But in this work, we've made the entire environment actually be fully differentiable. It's just one giant TensorFlow graph, and we're able to backpropagate through it over time. So because actually applying standard reinforcement learning methods in the multi-agent setting has some subtle difficulties that I will talk about in the next part of the talk. It's not as straightforward as it may seem. And also just to capture these communication utterances, because traditionally, like ideally you would like them to be discrete, like you're uttering one out of k symbols, but here you're in a setting where everything needs to be differentiable. So we just used Gumbel softmax estimator to be able to make these smoothed, discrete emissions. I don't know, Sergey, have you talked about these estimators? Okay, maybe I can talk more about it in detail if you're interested later. I would say in the grand scheme of things, it's not that important. So maybe for now, we'll skip this. A little bit about the architecture, though. Something that we were finding really useful, because you're in a setting now where there's multiple landmarks, potentially the number of them can be changing. There's multiple agents, and potentially the number of them can also be changing. And so what's the policy architecture that can support that? And there's various solutions that have been proposed recently. Something that we found to work well is to basically, in the observation, in the policy function, if you're observing multiple entities, like agents or landmarks, you process them with an identical set of fully connected layers, and then just do some pooling or softmax pooling, and that becomes kind of your feature vector that captures all of them. So you can have the takeaway is that you can have a dynamic number of agents and landmarks in the scene, and you don't need to retrain your policy. Yep.
When you say they have the same number, you mean they have the same weights?
Yeah, the weights of these FCX is the same. All of these basically procedures, or all of these blocks have the same weights, and similarly, these blocks have the same shared weights.
Okay, and they're not learning them independently over time.
They're not learned independently. They're shared. They are learned over time, but like all of them, yeah. Yes, yes.
So each input, so sorry, just to be sure, each input to these full connected layers is a different agent state. So like each agent reports its own state and observation, etc.
Yeah, that's right. So like this X might be like 2D position and color of the agent or the target 1, and then this is the color, like 5-dimensional vector of another agent. And similarly, this C is the communication utterance of agent 1, and this communication utterance of agent N, but it's processed in the same way.
So when you do the backprop, all the gradients go to everyone, basically.
Yes. So this is a setting actually where we have centralized learning, but in the end, after we've done the training, we have decentralized execution. So I think that's an important distinction that I will talk a little bit about later.
Okay.
But in the end, like what you have is after the training has finished, these agents only really interact with each other through the observations and communication and physical interaction. So let's see some of the simple languages that kind of end up forming out of this method. The first very simple task is, for example, if you have two agents and one wants the other to go to some location of some color, and similarly, like blue agent wants the red agent to go to the blue landmark, and similarly, the red agent wants the other agent to go to the red landmark. So the behavior you end up observing is they utter a particular like they meet, they can't, at the first time step, they don't utter anything, or at time step 0, they don't utter anything. But then they utter a symbol. And so here we've manually labeled them in this work just for ease of readability. So when we say here, this is like some abstract symbol, like 1 out of like symbol 4 or symbol 7. But if we give it afterwards, like post hoc, a labeling of blue and red or so, we can see that this communication pattern actually makes sense, because like what the agents are saying is just the color of the landmark from one to the other, and then they're going to that respective landmark that they've received. And the structure is consistent over over the trials. So this is kind of a consistent language that is being formed. Do you have a question? Or
yeah. So what have you tried? What happened if they have conflicting goals? Like they both want the other guy to go to that.
I will talk about that case later. Yeah.
So I have a question about, does the vision have any like meaning in this environment? Like, can the agents only observe what they see, or do they get the full state?
What do you mean vision?
You had the like lines.
So the lines are just for visualization of what the respective agent's goal is.
Of the locations of.
Yes. So they observe, each agent observes the locations of the landmarks and of other agents, but they don't observe the other agent's goal. That is private. So each agent's goal, like for example, if I want you to do something, that goal, you can't observe that goal.
Didn't you mention that the reward is global?
The reward is global. So the optimization objective is global, but the agents can't, but they won't necessarily be able to achieve that global reward. Like they don't get to observe the reward signals.
So what does it mean for an agent to want another agent to do something if there's just this one objective true reward describing how good it is for one agent to be in a certain location and another agent to be in a different location? Like if the reward function is a function of the state of all the agents,
Mm-hmm.
and it's shared across the agents.
Mm-hmm.
So then what does an agent wanting an agent, how is that?
Right, but the policy does not take as an input the reward. The policy just takes as an input an observation, which does not, my observation does not include your goals. So if I achieve it, I get a reward feedback, but I won't know ahead of time basically that I need to go there.
But this reward feedback will be omniscient.
Yes, but in the optimization, basically it'll be the feedback for how you should be updating the weights of your policy, but it won't be the feedback to the policy itself. But it won't be the input to the policy itself. I feel like, yeah, I think that's maybe a subtle distinction, and I'm not sure I communicated that
Maybe
well.
another way to say it is that at test time, there is no objective that's given to the agents in any way whatsoever. At test time, they're just running their known policies.
Yeah. Okay.
Yeah. Sorry, another question?
So how does the system deal with ambiguity when like you're only emitting one symbol per time step? Do you think you'd find like compositional language emerge if you had multiple emissions at one time step?
So that's next set of slides. That's kind of the cool thing is we do actually end up observing compositional language, and I'll talk about the details of like what exactly it looks like next. Yeah.
I mean, two quick questions. One of them is actually related to the previous question. So what is how do you ensure the necessity of communication? Like by defining a common goal, what stops from, say, the blue agent to observe, to basically be able to execute that, like realize that final goal?
Mm-hmm.
How do you ensure, how do you design basically the game in a way that
Right.
it necessitates communication.
Well, every episode is going to be different. So there is randomization so that for this particular episode, blue needs to go to the red landmark. But in another episode, blue might need to go to the green landmark instead. So it can't just memorize the strategy of like, oh, always go to red or always go to green. It needs to...
Why does that have to come from communication with another agent?
Because it doesn't, whether the indicator of whether it's blue or red that it needs to go to lives in the red agent's internal state. And that needs to get communicated somehow.
So there's some basically covered information that is necessary for...
Yes.
And that only, okay, I see.
Yes, yes.
And the second question was that, can you give us a sense of like kind of a dimensionality of this language that they develop, or how much capacity they are provided?
Yes, next set of slides will cover like, yeah, the size of the language and how it actually comes to be that way. Yeah, but all of these, yeah, excellent questions. Oh, I should also say one thing. So the 3 dots is basically symbol for silence because, so they just utter one of these, they just utter landmark identifier and then they become silent for the rest of the episode because there's a small penalty for making vocalizations. Just like you don't want to be saying like red, 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 red all the time. But because agents have internal recurrent memory, they commit that landmark location to memory and then just go to it without needing to have it repeated to them. Yes?
Is it possible here that they may learn some other communication if they can see their state by wiggling like bees do? And 2, in game theory, you would achieve some cooperative good outcome, but usually that comes from self-interest, not from a shared goal per se. So does that add ons with this approach?
Yeah, the formation of, yes, here we've kind of prescribed in an authoritarian way collaboration between all of them, and actually like emergence of collaboration is something non-trivial, and that is exactly in game theoretic ways, like in prisoner's dilemma settings. And I will talk about, hopefully there will be time, about a project that actually where the reward is not shared, the goals are conflicting, and out of self-interested goals, the collaboration does end up emerging, which I think is really non-obvious and cool. And to your first question, which is like is there nonverbal communication? I will also show some examples of nonverbal communication in the next set of videos.
Well, I guess I was thinking maybe they learned it without your going for it. So if you were expecting them to communicate with words, they might have found a secondary channel.
Yeah, so in our case, we're always, it seems like the preference was always to use words. And only when we actually took away the ability to use words, we saw the emergence. We saw nonverbal strategies, which I will talk about, like things like pointing. Instead of like pointing and guiding. B-wiggle. There have been various like debug versions that we've seen of B-wiggle strategies, but that's
Do you have any way of measuring how far this solution is from the optimal solution? Like, can you tell, like, I mean, if I were to run this numerical experiment multiple times, am I going to get the same thing? Am I going to get very different things?
Yeah.
Still do the job?
Yeah, here in this simple, like, I will show some more experiments later on to give you some sense. But in this one, it's a little bit suboptimal because what they end up doing at the first time step, like they don't know where to go. So they actually end up going to the midpoint of all of the landmarks. It's like, okay, I don't know where to go. I'm just going to go first at the first step to like where I'm closest to everything. And then they go to the right one. But if they knew the right landmark, they would just go to it from the start. So it's suboptimal because you need to hear it's like there's a delay time for communication. But it's not, as I will show, maybe I should just show like a set of results first to, I think, but all of these questions are basically anticipating what's coming. But the strategies, the communication strategies are pretty consistent. So you don't get suboptimality due to that, like, oh, they said the wrong thing and they kind of messed up. But it's just more like you can only be so good when there is this communication bottleneck and the associated delays.
I'd just like to confirm very quickly, the way that this goal is represented is implicitly by feeding in the some identifier for red to the red agent, and then through training it'll get from the goal that when it gets this first input red, it means that the blue agent should be going to the red landmark. It learns what it means in that initial input. It gets
as the goal, it gets just a 2D position of where it wants the other one to go to. It just gets a position vector. And so the policy then makes an association that, hey, that location is kind of actually coincident to a landmark. So that's a very good way to identify it. Also, because as I will talk about a bit later, the agents live in different reference frames as well, or it can be the case. So that, like, you can't necessarily talk in GPS coordinates because that could be like really one strategy. But if my reference frame, like my left is not your left, then that's where we see kind of this kind of absolute like association to landmarks. Yeah. Okay. Okay. Last question, and maybe I'll go to more results.
I think you have the communication cost. Do you consider other communication constraints like delays or like the range or something?
Yes. There is actually a few. There's like one constraint on communication, which is vocabulary size that I will talk about later. That is very important, and we also wish it wasn't there because it's a little bit of a phenomenological constraint. But I will talk about the details of that next. That's another big one. Otherwise, we haven't used any other constraints here. Okay, so maybe some of the couple of more examples of various languages under various settings. So in this case, didn't show. That's basically just a couple of other examples of strategies in this case where there's only one thing to do. It's like, yeah, they end up just basically saying the color of the landmark. But now if you have an environment where the agents have to do multiple things. It can either go to a particular location or it has a gaze location. And it might be asked to look at something. Well, then we end up observing actually this creation of words like verbs and the colors. So you'd have like go to red or look at blue landmark essentially coming out. And these are all, is it playing? Yeah, and these are separate words. So these different words are uttered in a sequence. And in the other settings, you might have 3 agents. Like, what if you have them needing to achieve multiple goals? Well, in that case, you also would have to identify the agent that you're sending the message to. So it's like blue agent, go to green landmark, or red agent, look at blue landmark, or do nothing. And so here, the ordering, I should say a couple of things. The words that ends up forming for red agent and red landmark, like they're 2 separate words in this case, and the languages that we see forming is actually kind of order independent, it seems like. I mean, some of the utterances have verb first and an identifier second. Some have it the other way around. So there isn't really a consistent syntax. I think like this is reminiscent of case marking strategies in language where you kind of have that be a separate, have red agent be a separate word. What's going on here? And so to answer your question with okay, is there any nonverbal communication strategies? If we take away, so we weren't seeing this if they could use language, they would always use language. But if we take away that ability, we're actually seeing that the agent ends up pointing towards, like, even though it doesn't need to move its gaze towards the location, it kind of moves it towards in the direction of the right landmark, and then the other agent is able to interpret that. Or if you can't use, if you also take away the ability to do pointing, you never know if it's when it's going to play. Oh. You kind of have these guiding strategies where the small agent wants the big one to get to the location. And so it actually ends up moving just to the side of it a little bit, even though it doesn't need to, as basically a way to get it's like, oh, hey, you should move to this landmark. Or when the ability to, when the big agent actually lost the ability to see the other one, like the agent is blind and can't hear, you end up basically seeing it's like, okay, the strategy is just to push the agent towards the location because there's no way to communicate with it. Was there a question?
Oh, yes. If you could assign different costs to communication modes, would they learn the relative value of being able to do one versus the other?
This is not something that we've tried, but I am very confident that that's the case. Like, yeah, if movement becomes, I mean, here at this point, like, there's really no choice. Like, kind of have to do that pushing thing to succeed. It's like kind of like pushing a puck in an RL experiment or so.
Sure, but for this example, you know,
like verbal versus nonverbal, you can do various trade-offs. Like, yeah, I'm pretty sure you could play with the costs of each to get one versus the other. Yeah. And so also you have this ability to generalize because you have this policy architecture that can take in an arbitrary number of landmarks and agents in the scene. You can take the setting where it was trained on just, say, 3 agents, and then execute it in settings when there's 5, there's still 3 agents, but 5 landmarks. And this is actually where you have like your conflicting goals question. For example, now there might be, you know, like 2 blue landmarks or so. And when the agent hears blue, in this case, it just ends up going to the midpoint of them, which I think is a sensible way to generalize. That's not the only way. It might, you know, maybe the right thing is just to go to one of the blues, but I think the important point is like nothing crazy happens. You actually end up seeing sensible behavior in this case. And also, you can generalize to more than, say, 3 agents. When the setting was trained with just 3 agents, this is kind of like at this point hard to see what's going on. But at some points, the agents might get conflicting goals. It might be asked to like go to red landmark. It might be asked to go to blue, and you know it still generalizes reasonably sensibly. Yeah.
So why not expand language to include some sort of directional notation? So say the left green landmark or the uppermost red agent.
Yeah, because this is a setting, this is purely a generalization test. This was, the agents have never been trained in a setting when there's 2 red landmarks or like 2 green ones. So this is just purely showing like, okay, what's like, just to show nothing crazy happens. I don't think you can expect any particular behavior here because like no training was ever done in this setting. So, but it's something that like, that's the next obvious thing to look into is like, yeah, if you do train in the setting with 2 greens, like what's going to be the way to disambiguate them? And that's where we think, you know, like words like near or far at that point, or like east, west, then would end up needing to be created. Was there another question?
I was basically just going to ask like what the next step, like what you just said the next step was basically like you create new words at runtime by like like looking at stuff and like, can you like introduce agents and that kind of thing?
I think that would be, so by that, do you mean like learning of new words at runtime?
Yeah,
like,
say you have like two countries with separate populations, like would a sort of merged language, like appear if you like had to happen to use common task after introducing them?
I think that would be really, really interesting to look at. And we've had so there's going to be a preliminary project on teaching that I will talk a little bit about before the talk ends, that will be getting at some of that. Like if now you have the ability to agents to teach about, say, the rules of the world, or like give examples to each other at runtime to teach new concepts. We haven't explored then tying it back to language. It's like, oh, how do multiple populations of agents with multiple languages, how will they interact? But that would be really, really interesting to look at. I think another very interesting motivation for it is that one of the populations can be human. So here we've had the setting where they were just communicating in abstract symbols, right? And they were still, like the structure, I think, looks like human language. You have like verbs and like verb arguments. But the exact set of symbols, like we can also communicate like either in Arabic or English, and that's kind of arbitrary. But then if you had some of the agents in the population be actually controlled by humans and speaking with a human consistent set of symbols, and the rest of the population that talks between it, like the rest of the population of AI agents also needed to be consistent with that human speaker, well, that would make the human-driven language like propagate through the rest of the population, or at least like that's what we hope. So I think that's a very important part. Do you also maybe I'm not sure if the other case that you meant with learning at runtime, it seems like also a very, very cool thing would be to acquisition of new words at runtime. So for example, like if I tell you like this is bloop, and then next episode I tell you like give me bloop, like you'll kind of remember what it is. That would also be really, really, yeah, great to look at, but we haven't looked into that in this particular work.
Is it necessarily the case that the different agents are using the same symbols to mean the same thing? That the languages are the same?
It is the case here. Yeah, that's something that I forgot to mention. So the policies of all the agents are shared. So it's like the agents are using the same brain wiring. So they do converge on a consistent set of symbols to communicate with each other. And that's not going to be the case in decentralized populations. And we'll be looking at, I think there's enough time. We'll be looking at decentralized settings very, very soon, very shortly as well. I'm just going to plug in my laptop for a moment because it's running out of battery. But also one interesting thing to look at was actually the word usage, or the size of the vocabulary that ends up being created. And we actually see that the size of the active vocabulary does end up settling to the size of the task at hand. So if you only need to communicate, say, the colors of 3 landmarks, we see that the size ends up actually converging just to overtraining iterations to exactly 3 symbols being used, and the rest of them are not being used. And we can see that before training, basically over time, the symbol emissions are really, really chaotic. It's like the agents are just like randomly uttering symbols. This is kind of averaged over all the different episodes. But you see that after training, actually, the symbol emissions end up being pretty stereotypical. So you do end up kind of converging on the same communication strategy. And so what led to this particular word usage, and that brings me to the constraints that we're finding to be quite important, which was, this was proposed by evolutionary linguistics people, and it's more of a really a phenomenological constraint that says basically has get richer dynamics for word populations. Like the word is more likely to be used if it's already been more used in the past. So it's basically like very similar to, say, Dirichlet process dynamics. But it's a little bit unsatisfying, and this is actually what has led to the creation of compositional languages that we end up that we saw. Where we saw it's like either a word for red or like separate words for verbs, because before that we're seeing more of holistic strategies. Like here, the environments really are fairly simple here, where you could get away with just using one word for like red agent, go to blue. That can all be one word. But with this particular pressure to have basically population sparsity for words, you end up kind of artificially limiting the language. And we wish we didn't have to do that. There are other reasons, or there are other proposals in evolutionary linguistics for why we have compositionality. One of them that's been proposed, I'll get back to your question really soon. One of them that's been proposed is, for example, the iterated learning model, where you're modeling actually the process of the language being taught across successive generations. And because between any two generations, you cannot possibly communicate every possible word, like every possible concept throughout the agent's lifetime. There are just too many. You have a poverty of stimulus. So students B will only get exposed, like we will only, as speakers, we will only get exposed to a very limited number of utterances throughout our lifetime from the previous generation. And so this creates the pressure for the language to be effectively and easily learnable. And that's where they show, and that's the argument for why compositionality and recursion in languages arises. And these have been studied actually with humans. There have been experiments where you have kind of these set of concepts. You might have like a color or a shape or a particular motion to a concept. And at first, the language starts with just random names for them. And the human subjects only get to observe a very limited subset of all the possibilities. And then they have to communicate or teach that to the subsequent generation. And over multiple generations, we actually end up seeing with human subjects that you have kind of compositionality in the words where like pilu ends up, I think, like being a set of like a subword for like circular motion and such. So I think that's a really interesting experiment. People have tried to recreate this computationally, but not with deep learning methods. There was quite a bit of hand coding or like hand design that was necessary to make that happen. So I would say experiments with iterated learning model were, in my mind, a little unsatisfactory on the computational side. Sorry, I think there were a couple of questions. You've had one?
Yeah, so not really a question, but it's like more of a perspective. It's like I don't think that your like teaching prior is like particularly artificial, right? Like what you're basically saying is like there's a prior over how much memory an agent has. I mean, so to contrast with ILM, like since I like only read papers now, I only know 3 words. Like therefore, GANs formally. Within a generation, you end up with words.
Sorry, this was too funny. Sorry, what?
Basically, the idea was like within a generation, you lose words. So basically, your DP, like your Dirichlet process is like a prior over memory that an agent has.
Yes, but I would say it's right now we had to artificially set it to be really, really constraining. Like the weight of that prior needs to be, I think, comparatively quite high, because like we'd like to have agents that have, like, we can have agents that have more memory capacity than in these experiments. Like, we certainly want them to have vocabulary sizes of more than 9. We want them to have large vocabularies, and it's just that the environments are so simple they don't require it. So we could, we could play that game where we just like make that prior have less weight, and we could basically control the effective vocabulary size that will be coming out through that weight. It's just, I think conceptually it's a little bit unsatisfying, because
yeah, I see what you're saying. It's like evolution didn't happen so that there's no constraint on brain size.
Yeah. I think that paper is just mostly like describing the phenomenon, but it doesn't. It wasn't saying like why that phenomenon comes about. Okay, so in some time, yeah, I think there should still be enough time. In the remaining time, I've mostly talked about model-based, centralized learning methods, and so this backpropagation through time approach, we found it to be pretty effective because you didn't have any of issues that arise with variance that comes out when using policy gradient methods. So we didn't need to worry about any of those issues, which was nice. We could just focus on this investigation of how language comes about. But it's unsatisfying because we could not model the process of agents learning from each other. Like, you could not do this. Like, you could not model how the how the language is learned, because the training was centralized and everybody was sharing the same policy. So it's like multiple clones just coming up with the same language, and they all had the goal like for this shared cooperation. So cooperation would of course come about, and because it was model based, it could also can't really incorporate external agents like human agents, because you would need to be able to backpropagate through the agent, and you can't really backpropagate through a human very easily. So that brings me to some of our efforts on model-free, decentralized learning, because part of the reason is that some of the real-world settings will only be partially cooperative. Like, if you have a fleet of cars, some of them might be able to coordinate, but then you will have agents like other cars driven by humans that you really can't assume very much about or can't control. But agents still need to be able to learn effectively in the presence of these other agents. And one of the findings that was a little surprising to us is that independent learners don't actually seem to coordinate, or at least like in our investigations that we've tried. So even if you have this very simple example where you just had 2 agents, speaker and a listener, and the speaker just need to say like the color of the landmark, like green, red before, and the listener just needs to go to the landmark. What we're seeing is that like we've tried a whole range of algorithms like DDPG, actor-critic methods, TRPO, Q-learning. Even this very, very simple strategy does not come out of the box in independent learners. And also what I mean by independent learners, like, so now every agent has a separate policy, every agent has a separate reward function, and each of them are running their independent algorithm. Like the agent is running, TRPO or DQN or something, and gathering experience independently. So what are the difficulties? Some problems is that the environment is non-stationary with respect to any single agent, because the agents are always learning. So you can't basically you can't rely on agents acting in the same way across iterations, because like suddenly they're changing their behavior and you don't really know how to, it's hard to learn in the presence of that. Furthermore, with Q-learning based methods, experience replay becomes difficult to use because, you know, if you had like an experience tuple of like state, action, next state, just with respect to your action and your observations or state, well, that tuple, like in previous iterations, like you always, currently you can always assume that that transition is going to, like it may be stochastic, but that's the transition that would happen across all the, like as the algorithm progresses. So you can end up using experience replay. But because the agents might be changing their policy, in the later iterations, you might not be able to use that that piece of experience because it might not make sense anymore. Like if you've said one thing earlier in the iterations, the agent might have done one thing, and later in the algorithm, later in the iterations, it might do something else. So that's hard to use. And the reward also, each agent's reward depends on actions of many other agents. So that leads to very high variance in the gradient estimate. And it makes credit assignment even more difficult than it already is. Because if my reward, like if I want you to do something, it might depend, you know, like it might depend on your behavior that is outside of my control, and that's, I may be making some actions, but like you may be making other actions, and it kind of becomes a chicken and the egg thing. So something that we were finding, one way to get around it, it's not the only way, but it's, I think, to continue the work that we want to be doing, I think this approach works well enough, where we create an actor, we have an actor-critic architecture where the actor only acts, where the actor only gets to observe the local, like only gets the local observations as it normally would in independent learners. But the critic actually gets to see global information from all of the other agents. And so that makes, actually, it makes it possible to use experience replay in this setting, because now the conditioning is happening over states and actions of all the other agents, and the experience tuples really don't change. And so that ends up succeeding at the simple coordination game. But you can also play kind of mixed competitive cooperative scenarios. So here, if we saw kind of like a simple deception scenario, where basically the goal of the blue team is to have one of the agents covering the green landmark, but they don't want the red agent to get to that landmark as well. So what they end up doing is both of them end up going to both of the landmarks to make it hard for the red agent to guess what the right one is. So it's kind of like simple deception strategy. And we also actually saw creation of very like simple cryptography, but that was a little bit, I would say, I think it's fair to say a little bit more contrived, because they could kind of pass a message ahead of time, and then they would end up kind of using like very simple like XOR encryption when they're doing communication. But I think this kind of physical deception is interesting, and that's what like the algorithm, the multi-agent version of DDPG does end up finding the strategy. Whereas like standard DDPG and standard TRPO had a lot of trouble. And I was really surprised by this. Like we've ran pretty large batch sizes. Several people have independently tried, have done these implementations. So yeah, I think it was surprising just how badly I'd say the standard methods were doing in these coordination tasks. You can also kind of create these simple like predator-prey games. Here it's a little bit harder visually to tell what's going on, but in terms of like quantitative metrics, the M80DPG is more successful. Something that we were actually finding very important as well is, or that we observed was overfitting now. Yeah.
So in this case, do you have like n critiques and each critic takes like 2 inputs?
Yes. So you have however many agents there are. You have this many critics. And there are separate critic policies, and they take in basically the global state of the world. But so it takes in observations and actions of all the other agents as an input to the critic.
So this one's scalable.
Sorry?
So there's not going to be scalable.
So I think there's many. In this case, we didn't do any tricks to make it scalable. I think there are ways to make it scale. I mean, you could, one trick is like you could do it at the level of the architecture, like play some tricks where there's weight sharing and such to make the critic network scale nicely. I think the other one that is more interesting, and we're actually exploring that right now, is that you may not need everybody's state for this algorithm to still succeed. And actually, it seems like throughout training, there's propagation of information happening. Like even if you have the critic dependent on the subset of agents, and even if it's a random subset, it seems like the training can still succeed because the information can propagate through the iterations. Yeah.
So both here and in the first algorithm, not M80DPG, but the first one where we had the shared policies and the shared reward.
Mm-hmm.
Yes. You still had joint training,
mm-hmm.
right? And then only when you had completely separate training, that didn't seem to converge because of the non-stationary environment.
Mm-hmm.
So both of these handicaps relative to the cheating version, which you mentioned at the very beginning, where you have the full state vector of all the agents, basically everything's the same agent. Since that's already also joint training in effect, what are we really gaining by giving ourselves this handicap here?
So I'd say the big gain, yeah, that's a good question. I think the big gain is that this is model free now, so that you're not assuming that you can backpropagate through the other agent's policies, or you're not assuming that you get to, basically, you get to have access to the other agent's policy function. So that's what makes potentially like the interaction with humans possible here. Whereas in the centralized training, so this is, yeah, I think it makes it possible for you to model the process of agents getting trained independently, even though they still get to observe extra information. Like that bit is a little unsatisfying, but they are still being trained independently, and they're not assuming anything about the models of the other.
So presumably there would be still okay behavior, even if we swap at test time one of the policies of one of the agents with a different policy from somewhere else. It still does kind of the right thing.
If you replace it with a policy.
But what I'm trying to get at is, what is the effect of not being able of this handicap,
mm-hmm.
not getting the policy during training?
So interaction with other policies, basically, and again, like interaction, like learning, being able to learn in the presence of other agents that you don't know anything about, because like you're only basically sorry. So the limitation is that you get to observe what they would observe. Like that's kind of the cheating part, and you get to observe what actions they make. And you could potentially like you could see a world where you could be modeling that, right? Like even if you, so right now you're assuming ground truth access to it, but you could try to infer that. And then yeah, it's a very different setting. I think another one is like you can also do mixed competitive, like you can have adversarial settings, whereas like in the fully centralized case, like you can only do cooperative because it's just one joint optimization. Yeah.
What happens if you drop your independent learner into a situation where you've already pre-trained a bunch of your centralized learners? Because it seems like one of the big problems is that if you're all of them are independent learners, the policies of all of them are constantly changing. So, but if you have already had a situation with a bunch of pre-trained centralized learners, then maybe you have more stable environment dynamics, and you can actually learn to cooperate with those agents. And that might be more similar to like actually cooperating with humans.
Yeah. I think that would make a lot of sense. Yes. I think maybe the pragmatic motivation is just to have that, like, then you kind of have to build maybe either two separate environments, or you need to create a model-based environment anyways, and that's like a lot of extra effort. Like one of the other motivations is that you don't need to create a model here anymore, and it was just, in terms of implementation, also really unwieldy. Maybe I'll just, because we're running out of time a little bit, maybe I'll discuss a few more things, and if there's any other questions, we can kind of talk about it afterwards. I'll be around. But I think one of the other interesting points that we're observing was overfitting here, and so much like in traditional machine learning, you might be overfitting on your data set, but then be doing very poorly at generalization on a test set. And so here we're seeing that in multi-agent settings, agents end up overfitting a lot to the particular strategy of the other player. So if it's an adversarial setting, like you might be creating a strategy that exactly counters the other player, but it's very, very brittle, because if something different happens, you really you weren't really trained for that, and you end up doing, if you have to interact with another agent, you end up doing very, very poorly. So one solution to this was to be training against an ensemble of agents. So you keep training an ensemble of policies, and in any particular episode, you might pick any two elements of the ensemble, like any two kind of random agents, and then they have to play nice, either adversarially or cooperatively against each other. And we're seeing that this kind of regimen, these agents that were trained end up being much more robust, and they end up performing much better against agents that were only just trained against one other opponent. So yeah, I think that's a very interesting case of overfitting that has come up in these multi-agent settings. So we've also tried it recently on more detailed physical environments, where here the motivation was this is, humanoid with TRPO-like methods always look weird, so I don't know. I think let's not speak about that too much, but I still think there is interesting strategies that do end up coming out, like various blocking or pushes. So here it's the goal is to prevent one from going to another, soccer, or get the other one out of the ring, and you end up kind of creating some simple things that can be interpreted as deception or faking out the opponent. Not sure how much of it is intentional, really, but I think it's an interesting sign of things that could be coming. It's also interesting that the skills do transfer. So even if we don't care about this wrestling environment or so, an agent that has been trained in a wrestling environment, if it's now put in an environment where it's kind of getting pushed with wind forces or such, it's actually able to withstand that versus an agent that wasn't. So I think this particular example is pretty simple, but down the road, I think that could be very interesting and very, very powerful method of creating just, in the end, intelligent agents. This, gosh, I really don't have too much time to talk about it. Very briefly, though, I think one interesting aspect as well is that modeling the learning process of other agents, that's something that we've tried to look at, where you're kind of assuming, like in the standard settings, you're always assuming that the other agent is just maybe a changing part of the environment, but you don't really assume like how it's changing, like how the agent is learning across, how other agents are learning across iterations. But something you can do is you can actually try to model that you can say, oh, the other agents are also running policy gradient updates. And something that you can do is you can backpropagate through them, and you get actually now basically having to estimate something like the policy Hessian, which is very high variance, and it may not be the best way of doing things right now, but I think in simple settings, what it's hinting at is that for games like Prisoner's Dilemma, where you might have, out of self-interest, you actually, like defection ends up becoming a dominant strategy. But if you can model that, if you can say, if you're modeling that, oh, hey, other agents will be changing in this way if I do this, we actually end up seeing a cooperation emerging and basically tit-for-tat strategies emerging as a strategy of choice in these repeated games, which I think is very interesting. So it's like here the cooperation is not prescribed and it's not the inevitable outcome, but it still ends up it ends up coming out when you're doing this extra modeling of others. Similarly, teaching is something that you can look at by trying to say, in this case, we only looked at like, oh, what examples can you give to other agents, say to describe a rectangle or others. And so some examples basically might be better than others. And so we're modeling again, also the learning process of the other agent and then of the student, and then saying, what examples can I give if the student behaves in this way, such that the student is able to perform on the task very well. And so we end up with pedagogical examples doing a lot better than getting just random examples as you would during normal training under a various kind of set of, for various teaching, for various concept teaching and for ImageNet hierarchies. And we end up seeing, we're actually running the experiments on humans, these automated teachers end up teaching humans, at least humans on Mechanical Turk, much better than random examples as well. And so the motivation is that we could potentially be using this to teach language. Yeah, I think that's kind of about it. Thank you. Sorry, it was a little bit over and kind of had to rush at the end, but hope that was interesting. And I guess we're out of time, but I mean, I can hang out here if there's any more questions, or I don't know. Yeah. If you want to ask a question.
Two quick questions. By the way, great.
Oh, thank you.
So the last result that you showed on human